All right, y'all. So today we have another new topic, 2.9 notes, physical connections. Get this in your notebooks, and then we will be talking about motion, position, velocity, and acceleration. Okay, so what I want you to do to start is I just want you to listen, to watch as I go through these definitions. These are from physics. We should all be somewhat familiar with these definitions. I want you to listen, watch, and then when I'm done, I'm going to give you a moment to write these down in your notebook because it is very important that you have them in your notebook. But for now, let's just go through these together. Okay, so what do the concepts of position, velocity, speed, and acceleration have to do with the calculus that we've seen so far in this class? Well, that's what we're going to learn today. So first we need to kind of go back in time and remember from physics, what are all of these things? So what is the position? The position's often labeled in calculus. Position is often labeled as x of t, and it gives the position of an object relative to the origin, and the origin just means starting point. So position of an object relative to the origin as a function of time. And that's why t is your variable. This is a function of time. Okay, so it just gives your position at a certain time. Now let's go through velocity. Velocity is often labeled v of t. It tells you how fast something is going and in what direction it's going. You need to know this, that it's both how fast something's going and the direction that it's going at an exact instant, at an exact time. It tells you how fast the position is changing with respect to time. And that might sound kind of familiar. The change of position with respect to time, we would call that in calculus the derivative of position. This is the change in position with respect to time. That's what the velocity is. So please make sure you note that velocity is the derivative of position. All right, cool. Now speed. Speed tells only how fast something's traveling. It is the absolute value of velocity. So write down this equation. Speed equals the absolute value of velocity, and remind yourself that this means make it positive. Absolute value means make positive. Whatever's in here is going to turn positive. All right, and last we have the acceleration. Acceleration is often labeled a of t, and it tells you how fast something is speeding up or slowing down. And I would love for you to write, this is the instantaneous rate of change of velocity at an exact time. It tells you how fast something's speeding up or slowing down at an exact instant. You could also think of it as how fast the velocity is changing with respect to time. And that again sounds like a derivative because it is. Acceleration equals the change in velocity with respect to time, which is the derivative of velocity. So make sure that you get that down. Acceleration is the derivative of velocity. Okay, I want you to take a minute, write all of this down. As you're writing it down, think about how I explained it and try to let that sink in. It's really important for the free response questions on the AP exam that you know all of these things and you have a deep understanding between the relationship of position, velocity, speed, and acceleration, and how they relate in terms of calculus. Okay, so write all this down. Cool, now that we've got that down, let's go ahead and move on. I'm going to teach y'all how I kind of like represent these relationships, and we will come back to this over and over throughout the year. So make sure you actually get this on your paper and in your notes, and let's get started. So what we're going to do is we're going to start by writing position, velocity, and acceleration, but we're going to write p or x of t, v of t, and a of t. So let's go ahead and do that. And we're going to like leave some spaces intentionally. So you're going to set it up like this, x of t, and then leave a space, a little bit of room, right? V of t, leave a little bit of room. And then, right, let's see. I'm trying to keep our colors as they were above. A of t. Okay, we are going to come back to this, like I said, over and over again, and we're also going to build onto it. But for now, we're focusing on one thing. How do we go from left to right? How do we start with position and get to velocity and then get to acceleration? So what we're going to do is draw arrows to represent that we're going from position to velocity, and then we're going from velocity to acceleration. And then how do we do those things? That's what we're going to write down. So let's make a note. This is how you do those things. You take a derivative with respect to time. So what is this saying? This is saying that to get from position to velocity, you are going to take the derivative of what you started with, derivative of position with respect to time. And then to get from velocity to acceleration, you're going to take the derivative with respect to time of velocity. You're going to take the derivative of the v function. Okay, cool. Let's go ahead and write down some like example units because this is really important to kind of know how the units change. So these are just going to be examples. So like be aware of that. There are a lot of units that we will see in calculus problems, but a common unit for position is meters. So let's go ahead and write meters. Let's pretend that position is in meters for this problem. That would mean that velocity is meters. And then because you're taking the derivative with respect to time, you're going to get per meters per second. This can also be written meters per second, right? Like that's how you're used to seeing it in calculus or in physics. But it's the same thing to write it kind of as a stacked fraction, one on top of the other. All right, and that means if we have meters per second and we take a derivative of meters per second to get to acceleration, we get meters per, and now you took another derivative with respect to time, so we get another time unit on the bottom, so we get seconds squared, which you also might be used to seeing as meters per second squared. Okay, this is what you need in your notes for now. I'm just going to let you know that we will be adding to this. We'll be adding arrows kind of like going this way. And then talking about how we go backwards. How do we work backwards from these functions? But for now, let's just talk about forwards. Okay. Key point is to get from position to acceleration or to velocity, you take a derivative. Then to get to acceleration, you take another derivative. All right, let's move on. What else can these physical functions tell us? All right, we've talked about how position tells us how far we are from the origin. I wanted y'all to be aware that the origin is usually the point 0, 0. And if we like think of a graph, that's the point right here, right? But our x-axis is time because we're talking about like real life scenarios. We're talking about position. So our x-axis is going to be real time, and our y-axis is going to be a unit of distance, a position unit. So again, we could go back to our example of meters. All right, so the point 0, 0, that would be time equals 0, and distance away from my starting point. How far are we away from the starting point? The meters is 0. Okay, velocity can tell us what direction a function is traveling in. This is super important, y'all. So there's two options here. Make sure you write this table in your notes. And then make sure you're aware that this means velocity is positive. So you could also in the table write v of t is positive. Or this means velocity v of t is negative. And then, of course, this means velocity equals 0. All right, and we're going to talk about what does velocity tell us about the direction that a function is traveling in. Okay, if velocity is positive, I'm going to do this. There we go. Then, if you're traveling on a horizontal line, your object that's traveling, whatever's traveling, is moving to the right. Okay, if your velocity is positive and you're traveling on like a vertical, so here's the horizontal line, right? And then a vertical line is like this. So if you're traveling on a vertical line and your velocity is positive, your object is moving up. Cool. So right means, or positive velocity means you're moving to the right. Now, the alternate is negative velocity. And what do we think that's going to mean? Your object is moving left on the horizontal line. And a negative velocity on a vertical line means your object is moving down. Sweet. What about these situations? On a horizontal or vertical line, what if your velocity is 0? If your velocity is 0, that means you're not moving at all. So, standing still. And that's from physics as well. And it doesn't matter if you're on a horizontal, if you're traveling left and right or up and down. If your velocity is 0, you're standing still no matter what. Okay, in calculus, you have to know this. You have to know if velocity is positive, you're moving right or up, depending on the situation we're talking about. If velocity is negative, you're moving left or down, depending on like, did we throw a ball in the air or is a car driving left and right? So depending on your situation, you need to know what negative and positive velocity tell you. All right, and then acceleration can tell us how fast the velocity is changing. We kind of took a note about that already. Let's move on. This is a super important topic or point that you need to know for free response questions on the AP exam. So how do you tell if an object is speeding up or slowing down? There's just facts that you need to know. Here we go. If velocity and acceleration have the same sign, so you need to look at the velocity, the acceleration, and check the sign. If the sign is the same, then the object is speeding up. Cool? But if your velocity and acceleration have opposite signs, you're still checking the signs. If they're opposite signs, the object is slowing down. You could write these notes and just leave it at that, or you could put these notes and the table. I would encourage you to put the notes, the 2 notes at the top and the table. You will need to know questions, AP exam questions might ask you, is this object's speed increasing? And you'll have to check the sign of velocity, the sign of acceleration to answer that question. So you're going to do like a sign test. Let's go ahead and write that down just so we are aware. Do a velocity and acceleration sign test. If you're asked if the object's speeding up or slowing down. Sweet. Let's move on. We only have one more thing. Or 2 more things. Okay, breaking down language and vocabulary used in free response questions. So the AP exam loves free response questions on particle motion, which is what this is, position, velocity, acceleration, a particle's moving. So we're going to do our best to break down this language that is very common. You're going to go ahead and try to fill this out on your own. So what I want you to do is fill in the blanks with your knowledge from 9th grade physics. And you're going to be choosing from the words. I'll give you a word bank. Choose from the words time, position, velocity, acceleration. And then you'll see where you can see you might have to do negative, positive, right, left. Okay, you have a word bank. Try to fill in these as best as you can. Go. All right. Let's see how you did. Initially means when the time equals 0 or t equals 0. At the origin means when your position equals 0. At rest means when your velocity equals 0. At rest means you're not moving, your velocity is 0. If the velocity of the particle is positive, then the particle is moving to the right or up. We just took a note on that. If the velocity of the particle is blank, then the particle is moving to the left or down. That would be negative. I would have all of these in your notes. Put all of these statements in your notes. To find average velocity over time interval, divide the change in, this one was kind of hard. To find average velocity over time interval, you're going to divide the change in position by the change in time. And we'll do some examples of that. Instantaneous velocity is a velocity at a single moment. That's just a fact. If the acceleration of the particle is positive, then the velocity is increasing. If acceleration of a particle is negative, then velocity is decreasing. In order for a particle to change direction, the velocity needs to change sign. The sign of the velocity tells us the direction a particle is moving. Okay, now what type of things are we going to have to do? Here we go. These are the things you're going to have to do. So make sure you write down some notes on these. What are you supposed to do when you are asked for the, velocity at a specific time? If you're asked for the velocity at a specific time, you are going to find x prime, actually, let me write that down, v of t, that means velocity at a specific time, and that equals x prime of t, the derivative of position at that time. So you're going to find the derivative of position, plug in t. All right, if you're asked to find the average velocity, you're actually going to use an AROC, kinda. You're going to find average rate of change from A to B of the position function. So equals, you're going to do x of t, or x of b, sorry, minus x of a over b minus a. This is, x is the position function, and that's going to give you average velocity over the interval AB. All right, if you're asked to find the time when the direction changes, find the time when velocity changes sign. If you're asked to find the speed, take the absolute value of velocity. Speed equals the absolute value of velocity. So you're going to take the absolute value. Value of v of t. All right, what if you're asked to find the acceleration at a specific time? Well, the acceleration is the derivative of velocity. So we're going to say the acceleration at a time t equals v prime of t. Take the derivative of velocity. What if you're asked to find the average acceleration? You're going to do another AROC, average rate of change from A to B, but you're going to do it of the velocity function. And that's similar to what we did for average velocity, right? And the reason why you're doing like the average rate of change of position on top to get to velocity is because the derivative of position is velocity. So the slope of the position function is going to be your average velocity. And then here we're doing the derivative basically of velocity to get to the average acceleration. Over an interval. This is the derivative of the secant line that you're finding. AROC, remember, is the derivative of a secant line. It's estimating the average acceleration or the average velocity. Okay, We will do practice in class. Make sure that you have all of these notes so that you are ready to jump straight into practice. Good work, y'all.